This right here is just one of those millions of curves that helps you fall in love with mathematics, and this is quite often called as the 8 curve just because it looks like an 8. And well, this curve is represented by this equation, y to the power 4 equals y squared minus x squared. And since we're doing derivatives right now, an obvious question to ask would be, well, what's the derivative of the tangent to this graph here? Let's say, what's the derivative here? So, well, we know about this. This is a horizontal tangent, so the slope's going to be 0. But what about, let's say you take a general point. Let's say you take this point right here, and perhaps that's not so easy then. And in theory, you can always find, let's say, for this function, you can find a nice enough expression for y, and you can do that by solving a quadratic. So if you look closely, this is y to the power 4 minus y squared plus x squared equals 0. This is a quadratic in y squared. So this is y squared squared minus y squared plus x squared. If you solve for y squared, you get 1 plus minus. I'm just using the quadratic formula. So the square root of 1 minus 4x squared, all of this being divided by 2. And to get a function just for y, well, you will take the square root of all of that. And the problem with differentiating a function like this is that, well, there is no such problem, but this is just so long. Like, we would have to apply chain rule a few times. The answer is going to be a bit messy, but let's say by the end of this video we will develop an appreciation for a technique that will help us to solve problems like these. But before that, let's take a look at a really simpler problem than this. So let's take a look at y equals square root of x. And in particular, I'm not just going to look at y equals square root of x, I'm going to look at y squared equals x. So remember that y squared equals x is not a function in its own, since it does not pass the vertical line test. So if you wanted to draw the graph of y squared equals x, you might be just tempted to draw this bit, this half parabola, and you would say, I'm done, but well, you're not, since let's say if you had 4 in the x input, y can either be plus or negative 2. So you have 2 arms of the parabola. Both of them are symmetric, by the way. My drawing's a bit weird. But anyways, if you wanted to figure out the derivative, the slope of the tangent here, you would differentiate the function y equals square root of x. And if you wanted to, let's say, differentiate here, let's say you wanted to find the slope of this tangent, you would need to differentiate y equals negative square root of x. Otherwise, you won't get the slope that you require right here. And that's a bit of a problem. Even though this is a really elementary function, y squared x is not a big function if you even compare it to the 8 curve. You can always, in mathematics, in real life, see functions that get complicated very quickly. So let's try differentiating this function without performing algebra to arrive at these pieces of the function. So you have y squared equals x. Now the thing is that you could differentiate both sides with respect to x. So d over dx of this, and again d over dx of this. We know that this is going to be equal to 1. The derivative of x with respect to x, well, that's equal to 1. But what is the derivative of y squared? And in particular, the question that I want to put forward is that if we know the derivative of y, let's say it's dy over dx, then what is the derivative of y squared? And the answer to that is the old chain rule that we have studied. That's something that perhaps you are very proficient by now. If not, go and watch some videos, and that perhaps will make you better at chain rule. And the main idea that I borrow from there is that you can write d over dx of y squared, since this is a function in y, you can write this as d over dy of y squared, and multiply to that dy over dx. And that's the chain rule. And this is equal to 1, this thing we know. And now we also know that the derivative of y squared with respect to y, well, that's equal to 2y. And 2y times dy over dx is equal to 1. That just means that dy over dx is equal to 1 over 2y. And notice what this has given us. Now, if you come towards me and you say, hey, well, what's the derivative at this point? What's the derivative at, let's say, 4 comma negative 2? Well, I would say, okay, let's plug in y's value and you would get negative 1 over 4. And if let's say you wanted to find the slope at this point, let's say 4 comma 2, then the slope here would be 1 comma 1 over 4. And that's pretty interesting. And if you want to, you can always try to differentiate these separately and see whether you get the same result, and you definitely would. This sort of technique wherein you do not explicitly writing a function such that the independent variable is on the other side and the dependent variable is on the other side, let's say y equals some function of x directly. This is called as an explicit definition of the function. And if you wanted to, let's say, not do that, since like in an example like this, in an example of the h curve, that's not a lot good. That just gives you a very, very ugly expression. This sort of definition of the function y, we will call that to be implicit. And this technique that we deploy here, this a chain rule modified thing, this is known as implicit differentiation. For now, let's attack the 8 curve problem, since that's a lot more interesting. Now, let's say you wanted to figure out, let's take a point on this curve. Let's take the square root of 3 over 4 comma square root of 3 over 2. Let me just check that whether that point even lies there. Yes, it lies on this curve. Now, if you wanted to figure out the derivative at this point, what we are going to do is we are again going to apply implicit differentiation. So let's do that. So we differentiate both sides by x since we intend to figure out dy over dx. And so doing that both sides, now the derivative of the difference is equal to the difference of the derivatives. You do that. Now, again, you need to apply the chain rule, the modified chain rule that we use for implicit differentiation. So this one will become d over dy of y to the power 4 times dy over dx. This one's going to become d over dy of y squared times dy over dx minus d over dx of x squared. Well, that's equal to 2x. And now what you can do is you can say, okay, so we have dy over dx. That's what we want. So let's take all the dy over dx, the derivative terms on one side. So that just gives you dy over dx in common. That's being multiplied by the derivative of y to the power 4 with respect to y. Well, that's easy. That's equal to 4y cubed. That's just the power rule. Minus, notice this thing comes here and it becomes minus the derivative of y squared with respect to y. And we know that as well. That's equal to 2y. And this entire stuff is equal to negative 2x. Now what we can do, and that's pretty interesting, is we can just simply take all of this and divide it here. So you get negative 2x over 4y cubed minus 2y. This is just, if you clean this expression a little bit, this becomes x over y minus 2y cubed. And that is pretty interesting. Also notice one thing, that when you do an implicit differentiation, you might get terms of y within the expression, within the derivative expression, but that's not at all a problem until you know at which point you are differentiating. In the case of an explicit differentiation, you don't get that. You get a nice, clean derivative in terms of x. And if you just wanted to figure out the derivative at this point, just plug in those numbers and you will get the right answer. Now there comes another part to this problem, and that part is when you want to do higher order derivatives. Now, this is something which is just an extension of the idea that we have developed right now. So let's say you had the function y squared equals x squared plus 2x. Now, this function right here, this is under an implicit differentiation if you look at it. We know that we can easily find dy over dx. We can easily find y dash for that matter. So d over dx of y squared is equal to d over dx of x squared plus d over dx of 2x. Sorry, man. The colors changed abruptly. And now you can always do this. You can always write this first term on the left-hand side as d over dy of y squared times dy over dx. That is equal to the derivative of x squared with respect to x is 2x plus the derivative of 2x with respect to x, that's equal to 2. Let me just write the function again since I'm just cluttering up the space. This is the function, the original one. And we also know that the derivative of y squared with respect to y is 2y. So 2y times dy over dx is equal to 2x plus 2. Take 2y to the other side, cancel out the 2's, and you will get dy over dx is equal to, well, x plus 1 over y. Now comes the interesting part. If you wanted to, let's say, figure out d squared y over dx squared, you need to redifferentiate this thing. That's what higher order derivatives are. So you need to find the dy over dx of this thing, or you need to find the dy over dx of this stuff right here. Now there are several ways you can do this again. You can either apply the quotient rule here. Notice this is just a quotient. One function is x plus 1, the other one is y. Or you could have just taken this thing right here. You could have taken this, again, an implicit definition of dy over dx embedded here, and you could have applied the chain rule. Let's take the quotient rule path. So now d squared y over dx squared is equal to, you need to find d over dx of this, and this is where it gets a little bit confusing, but well, it's not. So remember, in the chain rule, in the denominator, you have the squared of the quotient, the denominator, so you have y squared, and then in the numerator, well, you first differentiate the original numerator, so d over dx of x plus 1 multiplied by y minus d over dx of y. Notice how careful I'm being with the operators right here, since it's really easy to mess up with them at this instant, multiplied by x plus 1. And now that's sort of a solvable derivative. That's quite a lot easier. So d over dx of x plus 1, it's actually equal to just 1. That's just a constant function with the coefficient being 1, so that's just 1. And this is being multiplied by y minus dy over dx. Well, that is something we don't have right now, multiplied by x plus 1 divided by y squared. This is d squared y over dx squared. I said we don't have the dy over dx right now, but let's just take it from previous hands. And dy over dx, well, we know that it's equal to dy over dx is actually equal to x plus 1 over y. Plug this value right in, and you get y minus x plus 1 squared over y divided by y squared, or 1 over y minus x plus 1 squared divided by y cubed. Implicit differentiation is really easy, just the chain rule applied in a different way. It's really interesting. See you in the next videos.